Assalamualaikum warahmatullahi wabarakatuh. Distinguished guests, participants, ladies and gentlemen, good afternoon and welcome to the Department of Mathematics, Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, Yogyakarta. Before we explain what the event today is, let me welcome our special invited guests who spared their valuable time to make this event so meaningful for us. Her Excellency Professor Indah Emilia Wijayanti, the Chair of Algebra Laboratory, Department of Mathematics, Universitas Gadjah Mada, the distinguished speaker of this lecture series, Professor Ahmad Erfanian, all participants of this lecture series. First, please allow us to give an overview of the program. This lecture series will be held 7 times. The first 2 will be on 17th, which is today, and 24 April 2022. The topic will be groups, probability, and graph. 3 lectures will be held in June, exactly on 11th, 18th, 25th June 2022, and the last 2 lectures will be held on July, 2nd July, and 16th July. The topic will be spectral graph theory and topological indices in algebraic graphs. There are 33 registered participants for this event with the following compositions: 14 lecturers, 11 master students, 5 doctoral students, and the rest are undergraduate students and alumni. And for the event, actually one of the registered participants is from China, and she will also share some of her results about graph theory next month in Algebra Colloquium. And we will also have next month one lecturer from Indonesia who will share about graph theory also in Algebra Joint Seminar. So for this month and next 3 months, we will learn together about graph theory at least twice a month. Next, we kindly invite the chair of Algebra Laboratory to deliver opening remarks and to open the program officially. To Professor Indah Emilia Wijayanti, please.
Yeah, thank you very much, Pak Uha. So good afternoon or good morning, for the participants and also for Professor Ahmad Erfanian. We're glad to have you here in this nice forum. Because of difficulty of time, we hold this event in Sunday, so we are sorry for this, but I hope we can learn many things today. Although we're in Ramadan and in Sunday, but we still have a good spirit to learn something. First of all, on behalf of the Department of Mathematics, I welcome you, and also thanks to your time and your lecture. We will organize this, as Pak Uha said, that 7 times, and attendance by students, alumni, and lecturers, and maybe another people who interested in algebraic graph. So the aims of this lecture series is to look at the research in this area, up-to-date research, because we know that you do this research very productive. You have many papers in this theme, and I think it is interesting for us to learn together, to study together, and maybe to find some open problems on an idea or topics to make a collaboration in the future, especially for the students, PhD students, maybe magister students also. They can find some interesting topics to do their thesis or dissertation. So, okay, you can start the lecture in a few minutes and so forth. Yeah, so I will end this open remark. So welcome again, and I officially open these lectures. So enjoy the lectures for all the participants. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Professor Indah Emilia Wijayanti had already opened this program officially. Next, we now ask all invited guests and participants to join for group photos. So please, maybe for a minute, turn on your camera and post your group photos. I think, yeah, 1 minute should be enough. Please turn on your camera. Some of you still preparing. Give us big smile because we will have a great lecture today. Okay, so be ready. 1, 2, and 3. Okay, thank you very much for all of you for joining the photo session. And yeah, I think that's all for the opening ceremony. Now we arrive at the main agenda. Before we start the lecture, there are some information for participants. And yeah, we will provide an e-certificate for all of you. But yeah, there is a requirement for that. So please join at least 5 from 7 lectures. And the attendance form is based on Zoom chat report. So during lecture, please write your full name followed by a question or comments in every session that you are joining. Then we can recap your presence from there. So once again, the attendance form is based on Zoom chat report. So during lecture, please write your full name followed by a question or comments in every session that you are joining. So no need to linger any longer. To Professor Ahmad Erfanian, please. Maybe 2 hours with Q&A session. I cannot hear your voice. Still mute. Sorry. Okay.
Can you hear me?
Yes, perfect.
Okay. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. It's my great pleasure to have a series of lectures for your university. I remember I visited your university some years ago, and as I remember, I have a talk or I had a workshop. I don't remember, but I know many of your colleagues, Dr. Jenny, Prof. Yuni. I saw her photos here. So yeah. I hope that, yes, thank you.
Thank you. Thank you.
How are you? How's your husband? How's your daughter?
Thank you. So, they are fine. Yeah. Okay. Thank you.
All right. So I had a very good memory of my visiting in your university. I think maybe 6 or 7, I don't know, some years ago. So I hope that we move to teaching face-to-face, and hopefully we have the possibility to give this series of lecture, not virtually, but just face-to-face in your university in sometimes. What I would like to mention here is to give, is not the new area, but it's important because the algebraic graphs is something between some branches of. So I will explain about algebraic graphs. Before that, let me just explain about my series of lectures. So as I don't know the name, is 90. Is 90? Yes, is that correct?
Yes. Yeah.
Yes.
Correct.
As is 90 mentioned. So my main subject is algebraic graphs, but in the 2 first lectures, this Sunday and the next Sunday, I will provide some just what I would like to do in these two lectures is to remind you some of backgrounds on groups and probability and graphs. So my main topics, of course, my main topics means that what I would like to do in this series is to give some new algebraic graphs and some new problems and conjectures, and hopefully at the end we provide about at least five projects between me and some of your colleagues and students, and we can start after this series of lectures some new researchers. And so this is my aim to do in this series of lectures. So as I mentioned, in the first two lectures, today and the next week, I will give something about groups, probability and graphs. In this lecture, I would like to remind you some known groups, some important groups, because when we talk about algebraic graphs, I mean graphs associated to a groups, we have to know more about the groups, because we want to give some relations between group theory and graph theory. So it means that we have to improve our knowledge about the group theory and the graph theory, and then combine together to define a graph associated to an algebraic structure, and then just move some properties from graph theory to group theory and from group theory to graph theory. In the second part, which includes 5 lectures, I will give some important algebraic graphs, and of course some new one to this series of at least 2 or 3 new algebraic graphs. And you know, when we're talking about the algebraic graphs, so firstly we have to check some algebraic properties for a graph. But the spectral graph theory, one of the important topics, which is something between graph theory and linear algebra. So I want to give a combination between linear algebra, graph theory, and group theory. So that's the one of my aim to give a spectral graph theory. And also we have some topological indexes, and we want to use them to also compute something in algebraic graphs. So this is the just outline of my talk. Now, first of all, let me give about the position, the situation of algebraic graphs here. As you know, if you take the mathematical sciences, right? We have 3 important branches in mathematical branches: pure mathematics, applied mathematics, and statistics. And most of our universities have a department of pure mathematics, and department of applied mathematics, and statistics, right? In pure mathematics, we have some branches of pure mathematics. You know, we have algebra, analysis, geometry, topology, and so on. So that's some main branches of pure mathematics. And similarly, we have some branches of applied mathematics, like numerical analysis, differential equations, dynamical system, operation research, control and optimization, graph theory, discrete mathematics, and so on. And similarly, in statistics, we have some topics like descriptive statistics, sources and data, sampling concepts, regression, data science, probability, and so on. So that's some branches of pure mathematics, applied mathematics, and statistics. Now, if you take algebra from the pure mathematics, so take algebra. In algebra, you know that we have some sub-branches of algebra, like group theory, ring theory, and also in group theory, we have finite group, infinite group, and in rings, we have commutative algebra, we have non-commutative rings, and so on, module theory. And also, if you take linear algebra, it's something about matrix, vector space, and so on. So take algebra and two sub-branches of algebra, in group theory and linear algebra. And in the second branch of mathematics, in applied mathematics, you can take graph theory or discrete mathematics. So I put graph theory. And in the third one, you may just take probability. So we have some topics from different branches of mathematical sciences. Some of them from pure mathematics and someone from applied mathematics and statistics. Now, let me combine some of them together and put a name for them. If you combine algebra and graph theory, then you will get algebraic graphs. So algebraic graphs is something between graph theory and algebra. Algebra is general name because in algebra you have group theory, you have ring theory, you have some algebraic structures like semi-group and many things. So relations between graph theory and algebraic structures. We can define a graph associated to an algebraic structure. So we can name algebraic graphs. That's the main subject of my lectures. Now, if you take group theory and graph theory, this is just some kinds of algebraic graphs. It's graphs associated to groups, because we may define graph associated to a ring or a module or vector space and so on. So one of important types of algebraic graphs is graphs associated to groups. So that's combining graph theory and group theory. Now, one of interesting topics is to give a relation between probability from statistics and group theory. So probability and group theory provide the probability group theory. This is the new area of group theory. The importance of probability group theory is that as usual, we use to divide. If you take a property for a given group, for example, if you take the commutativity property, right? So it's usual for us to divide groups as the commutative groups or non-commutative groups, or just similarly, we can say abelian group or non-abelian groups. So if you take non-abelian group, so non-abelian groups means that we have at least two elements which are not commute. What if you take two non-abelian groups? So you may have in the first non-abelian group, you may have just few elements which are not commute, right? But in the second non-abelian group, you may have many, many elements which are not commute. So it means that the first non-abelian groups, it's very close to abelian group because we have just few, maybe we have only 2 elements which are not commute. But the second non-abelian group is very far from abelian. So we can put a probability for non-abelian groups, which give a situation of non-abelian groups in this direction that is that close to abelian or far from abelian, right? So you may use the probability for some other properties in groups, like you may give a probability for property of nilpotency, solubility, and so on. So the combination of group theory and graph theory, probability and group theory is the probability group theory. Now, if you combine graph theory and linear algebra, so it means that you may give, you may associate some matrices to a graph. So combination between graph theory and linear algebra will give the spectral graph theory, right? Now, what we have to do is finally to give a combination of a spectral graph theory, probability group theory, and graphs associated to groups all together. So it means that we will have a group, we will have a graph associated to group, we may define probability to a group and just give a relation between probability and the graph associated to a group, and also spectral graph theory. That's it, just a very short description of my topics in just 7 lectures in this series. Anyway, now what I am going to give is to remind some basic concepts in groups. I know that it's very easy for you, and most of you know about the group, but just for maybe some undergraduate students, just recall these concepts. So I'm so sorry for professors and doctors and lecturers for just a few concepts of beginning group theory. Now, you know, because in this lecture, I'm going to give some backgrounds about the group theory. The first important topics of group theory is to define a group. So I will define a group, and then we'll introduce some important groups. You know, the binary operation means that if you take a non-empty set S, and if you have a function, we may denote by S star from S cross S to S, then the pair S and S star is called a binary operation. For example, if you take a natural number and if you put a usual sum, then you can see that the natural number and the sum, the usual summation, is a binary operation, right? And for shorten of notation, if we have a binary operation, right, S and S star, you know, when you consider operation S star from S cross S to S, so we will have the image of any pair, for example, X and Y, we will have a star of X and Y. So we may denote the S star of X, Y by X star Y. Now, if we put one more condition for a binary operation, if you put the associativity, right? If we have associativity, then we will get a semigroup. So semigroup is a binary operation and the associativity property. Associativity property means that the X star Y and then S star by Z is equal to X star and Y star Z for all elements X, Y, and Z in S. And also we may have identity and the inverse elements for a binary operation. You know the identity elements, if we have an elements, for example, E in S, such that if we have this property, X star E equal to E star X is X, then we can say that an element E is an identity element. And if we have identity element in a binary operation, then we may define the inverse of an element. So if X is an element in S, the inverse of X is Y with the property that X star Y is Y star X is identity. Now, we are ready to define a group. If we have a binary operation, right, S and S star, then we say that S and S star is this binary operation is a group if we have associativity property, if we have identity element, and if we have inverse. If we have three more conditions for a binary operation, then we can say that this binary operation is a group. We have many just simple examples. If you take integer numbers and just usual summation, then we can say that that integer numbers Z and plus is a group. And also, if you, so the elements of a group is not necessary to be integers. So if you take all 2 times 2 matrices with interest in integer numbers, and if you take the sum, the usual summation between 2 times 2 matrices, then we can see that the M2 times 2 of Z with the usual summation with plus is a group. If we have another conditions, one more conditions to a group, which is the commutative property, which means that if we have X star Y is Y star X, then we can say that for all elements X and Y, we can say that the group is commutative, or is known as a abelian group. Just few conventions about, or notations. You know, we usually denote a group by G because G is the first letter of the English word group. So we usually use a capital letter G for a group. And also we may just delete the S star between the the X, Y instead of X star Y, right? One more thing is that if we have a binary operation with the associativity and identity elements, so it means that if we delete the inverse from definition of group, then we can get monoids, right? So by this definitions, we can see that if we have a binary operation and with associativity, so we will have a semigroup, right? And if we add identity element to semigroup, we will get the monoid. And if we put inverse of any elements, having inverse of any elements, then we will get the group. And if we add a commutativity, then we will get the abelian group. Here is some examples about the groups, semigroups, monoid, and so on. So natural number with the plus is a semigroup, because what we have is only binary operation and associativity. We don't have identity elements and the inverse, because you know, identity elements in natural numbers is 0, and in natural numbers does not have the 0 elements. If we add the 0 to natural numbers, so we'll get monoid. You know, if we have the integer numbers with the multiplication, we will get the monoid. It's not a group, because we don't have inverse. And here is some more examples. So the 2 times 2 matrices with entries of integer numbers with multiplication is monoid. The rational number, it's an abelian group. The real numbers with the plus is abelian group. And also, it's interesting to see that we may introduce the summation under the modulo, for example, 4. That sum of integers in modulo 4 means that if we add 2 elements, for example, 1 plus 2 is 3. 1 plus 3 is 4, but because we have in modulo 4, it's 0. And 2 plus 5, you know, 2 plus 5 is 7, is 7, but in modulo 4 is 3. 3 plus 3 is 6, and in modulo 4 is 2. So by this summation, if we define Z4 consists of elements, you know, the bar means that when we say 0 bar means that 0 bar is 0, is 4, is 8, is minus 4. So all multiplication of 4 is the 0 bar. 1 bar means that we have 1, we have 5, 9, because the remainder of any of them by 4 is 1. So if we put Z4 is as a set of elements 0 bar, 1 bar, 2 bar, and 3 bar with the summation of plus in modulo 4, we can see that is a group because it's a binary operation. We have associativity, we have identity elements, we have inverse, and the commutativity. So it's an abelian group. And in general, we may introduce the group Zn with the plus in modulo n. So Zn is also an abelian group. We have some more notations in groups. You know, the centralizer of an element we may denote by Cg of x, and is the set of all elements y in G, which y and x are commute. So the centralizer of an element x is a subset of G. The center of a group, that we close. So the center of a group, we may denote it by Z of G, and that's the set of all elements like y in G such that y is commute with every element x in G. It's easy to see that the center of a group is the intersection of all centralizers of X. You know the definition of cyclic group. So first we can define group generated by an element. So if we have a group G and if we have an element X in G, so the group generated by X consists of all elements X to the n for all n for in the integer numbers. So that's the cyclic group and cyclic subgroups. And if we have an element in group G such that G is a group generated by X, then we can say that the group G is cyclic. You know that if we have a group G and if the center of group G is equal G, then we can see that it will imply that the group G is an abelian. And conversely, if the group G is abelian, then the center is the whole group. And if we have an element in the center, then the centralizer of that element is the whole group of G, and vice versa. And if we have a non-central element like X, then the centralizer is a proper subgroup. And you know that the center of a group is always a normal subgroup. You know the definition of derived subgroup. If we have a group G, then the commutator of two elements X and Y, we can denote by this notation, and that's the closed bracket X comma Y, and open bracket and close, we put X and Y into brackets, and we can divide the commutator of X and Y by X inverse, Y inverse, XY. And the group generated by all commutators is called the derived subgroups. All right. Now, what I'm going to mention here is to just remind you about some important groups. I'm going to introduce the symmetric group. First of all, you know the permutation. I want to introduce the permutation on a subset X. So if X is a non-empty set, then the function f from X to X, which is 1 to 1, is called a permutation on X. For example, if X includes two elements 1 and 2, then we will have two permutations. We may introduce two functions f1 and f2. F1 will take 1 to 1 and 2 to 2, which is the identity function, and f2 will move 1 to 2 and 2 to 1. We have two permutations. We may just give a notation for f1 and f2 as a shorthand notation, right? So we may put f1, this identity function, as by e, a small e, and f2 we can denote by a cycle 1, 2, because this is cycle 1, 2 means that 1 goes to 2 and 2 goes to 1, right? So we may have just permutation on set X contains elements 1, 2, and 3. As you see, we will have 6 permutations, right? So that's the identity permutation. The second one will take 1 to 2 and 2 to 1 and fix 3. And for the third one, one will go to 3 and 3 to 1 and 2 fix, and so on. So we have 6 permutations. And generally, if you take X as a set of elements 1, 2, 3, up to n, then we can see that we will have n factorial permutations, because if you take an element 1, you know, we have n possibilities for 1. So 1 can be moved to 1 or 2 or 3 up to n. So we have n possibilities for 1. If 1 goes to something, then 2 cannot be to that choice. So we will have n minus 1 choices for 2. And similarly, the number of choices is n factorial. Now, by this just notations, we can define the symmetric group Sn. The symmetric group Sn is the set of all permutations on set X, which X is 1 to up to n. So Sn with the composition of functions, because every permutation is a function, is just form a group, and we can give a name symmetric group. So if n is 2, the S2 symmetric group on 2 elements is identity and 1, 2. For S3, we have 6 elements. We have identity, 3 cycles 1, 2, 1, 3, 2, 3, and 1, 2, 3, 1, 3, 2. So we have 3 factorial 6. And similarly, for S4, we have 24 elements. In general, we can see that the order of the symmetric group is n factorial. Now, if you take a permutation, a cycle is a permutation, A1, A2 until AN. That is a cycle of length n, right? If we have a cycle of length 2, then we can give a name transposition. So transposition means a cycle of length 2. And we can see that every permutation can be presented as a multiplication of some transpositions. For example, 1, 2, 3, we can just see that 1, 2, 3 is the multiplication of 1, 3, 1, 2. You know, if you move from right to left, so 1 goes to 2, 2 to 2, so 1 goes to 2, 2 to 1, 1 to 3, so 2 to 3, and 3 to 3, 3 to 1, 3 to 1. So we get the cycle 1, 2, 3. And similarly, 1, 2, 3, 4 can be presented as a multiplication of 1, 4, 1, 3, 1, 2. So if we have a multiplication of even transposition, then we can say that the permutation is even. And similarly, we may have odd permutation. Now, if you see, for example, S3, we have 6 elements. So you can see that the even permutations of S3 contains elements identity 1, 2, 3, and 1, 3, 2. And odd permutation is 1, 2, 1, 3, 2, 3. Now the even permutation the even permutation will provide all properties of groups. So the even permutation is a group So we can give a name for the even permutation of the symmetric group by alternative group. So the alternative group, which we can denote by AN, is the set of all permutations or even permutations of SN, of the symmetric group. So we know that the alternating group on 2 letters is the trivial subgroup. The alternating group on 3 letters, A3, is a group of order 3. We have identity 1, 2, 3, 1, 3, 2. And the alternating group on 4 letters, we will have 12 elements, right? Because S4 has 24 elements. So half of elements of S4 are even permutation and the rest are odd permutation. So A4 has 12 elements. So we can see that in general case that the order of alternating group AN is in factorial over 2, is half of n factorial. Here are some basic results about the alternating group. You know, alternating group is a normal subgroup of the symmetric group, the center of symmetric group, and also alternating group with the just for n at least 3 for symmetric group and n at least 3 for alternating group. The center is trivial. The derived subgroup of symmetric group is AN. The derived subgroup of AN is AN, and also the quotient group SN over AN is a cyclic group of order 2. And here is example about the center, about the centralizer, about for S3 and also alternative group. Now, let me move to the second important, the third one. The third, because the first one I introduced the symmetric group, the second one is alternative group. Now the third one is dihedral group. One of the important groups in group theory is dihedral group. Dihedral group is very important, and in many of algebraic graphs, we may use dihedral group. Before to introduce dihedral group, I can give a definition of presentation for a group. You know, we can define a group as a set of elements, or because sometimes the group is big, so the usual way to introduce a group is to define a group by 2 sets. Set of X as a set of generators, and R is a set of relations, right? For example, if you take a cyclic group of order n, so we can denote the group G by the set of singleton set A as a generators, right? Because the cyclic group can be generated by 1 element. And that's the relation, because cyclic groups of order n, so the order of n, A is n, so A to the n is identity. And similarly for the symmetric group, we can give a presentation for symmetric group. If you put A is 1, 2, 3, and B is 1, 2, so here we can get the presentation for the symmetric group. We have many properties, and it's one of important branch of group theory is the presentation of groups. So it's actually related to the free group. Right, now let me introduce the dihedral group of order 2 times n. So the dihedral group of order 2 times n, we may give the following presentation. So we can just generated by two elements, A and B. So A to the n is B squared is identity. So it means that A has order n and B has order 2. And we have this relation BAB is A inverse. If n is 2, so D4 is a group of order 4, you can see that we have these relations, and we can see that D4 is a non-cyclic group of order 4, which is we can denote by, we know that the the group of order 4, we have two kinds of groups of order 4. The first one is cyclic group of order 4. We can denote by Z4, and the second one, non-cyclic group of order 4, is D4, or we may put a name Klein group. If n is 3, D6 is a dihedral group of order 6. We have this presentation for dihedral group of order 6. And this is the 6 elements. Identity, A squared, B, A, B, A squared, B is exactly S3. For S3, we find just the same presentation. So D6 is S3. Now, how about D8 for n is 4? D8 is one of important groups, and in some graphs, the first example of an algebraic graph, we may consider S3 or D8. So this is the presentation for D8, right? D8 can be generated by two elements, A and B, and A has order 4, B has order 2, and that's the relation BAB is A inverse. We can see that the 8 elements of D8 is identity A squared, A cubed, B, AB, A squared, B, and A cubed, B. And here is the order of these 8 elements. So identity has order 1, A and A cube has order, they have order 4, and the rest, which A squared, B, A, B, A squared, B, and A cube, B, they have order 2. The center of the dihedral group contains 2 elements, identity and A squared. Now, how about the subgroups of dihedral group of order 8? The only subgroup of order 1, we have trivial subgroup. For subgroups of order 2, we have 5 subgroups of order 2. We have identity and A squared, which is the center of the dihedral group. And also, we have the group generated by B, or by AB, by A squared B, and A cube B. They are all subgroups of order 2. For subgroups of order 4, we have 3 subgroups of order 4. The first one is the cyclic group generated by A, right? Because A has order 4, so this is the one of subgroups of order 4, and we have 2 more subgroups of order 4, which is not cyclic, it's isomorphic to Klein subgroup. We have identity A squared B, A squared B, and identity A squared AB and A cube B. So that's the subgroups of order 4, and the next subgroup is the subgroup of order 8. We have the whole group, the dihedral group. So the total number of subgroups, we have 1 sub identity, and here is 5, so we have 6, 3 more for 4, we have 9, and plus the whole subgroup, the 8, 10. So we have 10 subgroups for dihedral group of order 8. It's interesting to see that the there is a formula for the number of subgroups of not only dihedral group of order 8, but also in general case for dihedral group of order 2 times n. For dihedral group of order 8, we have n is 4. So if you see it, the divisors of 4, we have 3 divisors of 4. You know, we have 1, 2, and 4. So we have 3 divisors. Now, if we add these 3 divisors, so 1 plus 2 plus 4 is 1 plus 2 plus 4 is 7. And we have 3 divisors, so plus the number of divisors. So 7 plus 3 is 10. So we can get 10 subgroups by the summations of the number of divisors and sum of divisors. And similarly, we have dihedral group of order 10. For dihedral group of order 10, the center is trivial, and the subgroups of order dihedral group of order 10, we have subgroup of order 1 is trivial. For subgroups of order 2, we have here is 5 subgroups of order 2, 1 subgroup of order 5, and the whole subgroup is of order 10. And we have 3 of them are normal subgroups. In general, the dihedral group of order 2 times n, we have this presentation for dihedral group of order 2 times n. So that's the group generated by A and B, which A has order n, B has order 2, and BAB is A inverse. So we have 2 n elements. You know, that's the set of elements. We have identity A squared, A cubed until A to the n minus 1. And BAB, A squared, BA cubed, B until A to the n minus 1, B. The center of the dihedral group depends on the number n. If n is odd, the center is trivial. And if n is even, then the center is a subgroup of order 2. Right. Now let me move to the number 4 of non-groups is the Quaternion group. Quaternion group we can denote by Q8. So contains 8 elements. So the elements of Quaternion group is 1, minus 1, I, minus I, J, minus J, K, and minus K. So we have the relations. We have I squared is equal to J squared is K squared is equal to minus 1. And we have these relations. If you have the cycles, you know, I, J, and K with this direction. So I times J is equal to K. J times K is equal to I, and K times I is equal to J. So by this relation, you can see that because A squared is minus 1, you can see A to the 4 is 1, and similarly, J to the 4 and K to the 4 are 1. So I, J, and K, and similarly minus J, minus I, and minus K, they have order 4, and 1 is the trivial identity elements, has order 1, and minus 1 has order 4. So that's the order of elements of Q8. And the center of Quaternion group is 1 and minus 1. You know, by this multiplication between I, J, and K, we can see that the Quaternion is a group. So 1 is identity, and you can see that we have all properties of groups here. So subgroups of Quaternion group of order 8, So for order 1, we have the trivial subgroup. Order 2, we have only one, which is the center. We have 3 subgroups of order 4, and the rest is the order 8, is the whole group Q8. So it's interesting to see that for quaternion of order 8 has this property that every subgroups of Q8 is normal. So Q8 has this property that all subgroups of Q8 are normal. No, we can give a definition in general for a given group G. So if we have a group G with this property that all subgroups are normal, then we can say that the group G is a Dedekind group. If we have a Dedekind group and the group is non-abelian, then G is called Hamiltonian group. We can give a presentation for quaternion group for Q8. So the presentation, if you put A as I and B is J, then you can get this presentation for Q8 generated by A and B. So A squared is equal to B squared, A to the 4 is identity, and B inverse AB is A inverse. Now, we can give a generalization for quaternion group. We can say generalized quaternion group. So the generalized quaternion groups, Q4, we can denote by Q4n, because the generalized quaternion group is a group of order 4 times n. So the presentation for Q4n, we have this presentation. That's the group generated by A and B. And we have these relations. A to the n is B squared, A to the 2 times n is identity, and B inverse AB is A inverse. You can see that if n is 1, then the Q1 is a cyclic of order 4. And if n is 2, then we can get the Q8 as I defined before. And here is some properties about some results, known results about the generalized quaternion group, is that the order of quaternion group Q4n is 4 times n, and the generalized quaternion group is an abelian group if and only if n is 1, and every element of the generalized quaternion group we can present these elements by just A to the A, B to the J, for I is between 0 and less than 2 times n, and J is 0, 1. The center of the generalized quaternion group is a subgroup of order 2, and the quotient group of Q4n over the center is isomorphic to dihedral group. That's the relation between dihedral group and the generalized quaternion group. And here is the elements of the quaternion group. We have 4 times n elements. You know, we have 2n elements here, A squared, A cubed, until A to the n minus 1. So we have 2n elements here. And we have another 2 times n elements for B, AB, A squared B, and A to the 2n minus 1 B. And there is a very nice theorem that says that every subgroup of the quaternion group is cyclic or is a generalized quaternion group. Now, the next known group is a semidihedral group. Semidihedral group we can denote by SD to the n, or sometimes we can denote semidihedral group by quasi-dihedral group. So we have two notations for that semidihedral group, or another name is quasi-dihedral group. So the presentation for the semidihedral group, we may use the just name semidihedral group. So the semidihedral group is a group presentation by two elements. A has order 2 to the n-1, and X has order 2, and we have this relation X is A to the 2 to the n-2 minus 1. The order of semidihedral group is 2 to the n, right? And for example, if n is 4, then we will have 16 elements here. That's the 16 elements. You know, we have A square, A cube, A to the 4 until A to the 5. So we have 8 elements here, and we have X, AX, A square, X until A to the 7 times X. We have another 8 elements, so we have 16 elements. Here are the order of these 16 elements, right? And the subgroups of semidihedral group of order 16. So that's a list of subgroups. So we have identity subgroup, we have the center of a semidihedral group is the subgroup of order 2. We have 4 subgroups of order 2 which are not normal, because of order 2, the center is normal, and we have, so we will have 5 subgroups of order 2. So one of them is the center, which is normal, and the rest are not normal. We have 2 kinds of subgroup of order 4. We have 3 subgroups, cyclic subgroups of order 4, and we have 2 more non-cyclic subgroup of order 4. And also we have subgroup isomorphic to dihedral group of order 8, and another subgroup isomorphic to Quaternion group of order 8. That's a list of subgroups. And similarly for n is 5, so we have 32 elements. The center has order 2, and you know the center of semidihedral group contains 2 elements, identity and A to the 2 to the n-2. Okay. Now, I'm going to finish the just introducing just these groups, and then just start the probability. The 7 kinds of non-groups is the general linear groups. So if you take ZP for P prime P, you know that ZP with the plus and multiplication in modulo P. So the general linear group we can denote by GLNP, and that contains all n times n matrices with all entries in the field ZP, and the determinant of this matrix is not 0. So you can see that this n by n matrices with the multiplication between n times n matrices forms a group, and we can say is a general linear groups. The order of the general linear groups, as you can see, is this number, and that's the center, and the order of center is p minus 1. The last one is a special linear group. A special linear group is just subgroup of general linear group. So if you take again all n times n matrices with entries in ZP, but the determinant is exactly 1. You know, for general linear group, the determinant is not 0, but here we may have the determinant is exactly 1. So this subgroup, which can denote by S, L, and P, is called the special linear group. And here are some orders of some examples. For example, GL22 has order 6, and you can see that GL22 is isomorphic to S3. GL23 has order 48, and the center of GL22 is 1. The center of GL23 is 3 minus 1 is 2, and also the quotient group of SL23 over the center of SL32 is 42. Right, now I'm going to move the second part of today's lectures. You know, I just introduced some groups. I know that it's very just elementary concepts in group theory, and I'm sure that all of you know about it. But just I want to give my notations and just a few reminding of these concepts. Now I'm going to give the probability. What's the definition of probability? You know, if we have an event, so the probability of an event, is defined just the number of ways which can be, the event can be happen, but the total number of ways, total number of outcomes. So if A is an event, so the probability of having an event A is the number of ways A can be happen divided by the total number of cases. For example, if you take a dice, we have six numbers on every face, right? So I put three events here. An event A is having number 1, B is having numbers 2 or 5, and C having an odd number. So the probability of having an event A, so the probability that we have number 1, so if we take a dice and put to have number 1 on the top, so we have only one case, and total case is 6. So the probability is 1/6. For event B, so we should have numbers 2 or 5. So we have 2 cases from 6 cases, right? So the probability of having an event B is 2/6. And for C, for the just odd numbers, we have 1, 3, and 5. So we have 3 cases, and the total cases is 6, so 3/6. So that's it. Very just very elementary definition of the probability. Now, I'm going to to combine probability and group theory, right? Let me give some very not important, just very elementary probability for a given group. Now, the first probability, I put the name P group degree. So what's the definition of P group? The definition of P group, we know in group theory, we can just define a P group in such a way that if the order of each element of a group is the power of P. And of course, if the P group is finite, it's equal to that the order of group is the power of P. But the main definition is the order of any elements has a power of P. So that's the definition of P groups. For example, if we have a group of order 4, is two groups because the order is 2 to the 3. Or if we have for example, Quaternion of order 8. So the order is 8 is 2 to the 3. So it's again 2 group. D8 is 2 group. But the S3 is a group of order 6. It's not P group because it's not 2 group or it's not 3 group. So we don't have just 2 groups or 3 group properties. Now, let me give a definition for P group. That's the definition of P group, which I mentioned to you. So we have a P group if order of any elements has a power of P, and in finite case is the order of group is P to the K. Here are examples about the P group. You know, the cyclic group of order 8 and dihedral group of order 8 are all 2 groups. And also cyclic group of order 9 is 3 groups. You know that, for example, if you take the cyclic group of order 9, you know, we have 9 elements, and you can see the order of elements. You know, in Z9, the identity elements has order 1. We can put 3 to the 0. 1 has order 9, because the Z9 can be generated by 1 is the generator, has order 9 is 3 to the 2. Or order of 2 bar is 9, again the order is 3. We know that's the just orders of all elements. If you can see each of them, the order order of each element has a power of P, is 3 to the 0, 3 to the 2, 3 to the 1. So the Z9 is 3 group. Now, let me give a definition about P group degree. So the P group degree means that if you take a group G, right? I mean, find that group G. What's the probability of a group G to be a P group? So again, let me just explain this probability. If you take a group G, so if all elements of the group G are a power of P, then G is a P group. But sometimes we may have not all of elements, is some of orders of a power of P, right? So if we take the number of elements which has a power of P divided by the total number of elements which the order of the group G, that's the P group degree So we denote the P group degree by dP of G. dP of G is the just number of elements like X, which that the order of X is the power of P. So the number of elements which has order of power of P to the total number of elements which the order of G. Let me just put a name for any elements which has order a power of P. We can put P element. P element, we can give this name for every element has a power of P. So the P group degree is the number of P elements divided by the all elements order of the group G. This is the probability of a group to be a P group. Let me give an example. Look at S3. So you know S3 has 6 elements. So we have identity 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So look at the order of elements of S3. So identity has order 1. 1, 2, or 2, 1.
Kental ya kayaknya.
Iya,
Oh iya, gangguan
kita
ini
tunggu
koneksi.
dulu.
Ini memang tadi suaranya sudah mulai ini. Ya.
Enggak, bisa nyambung lagi.
Ya.
Saya kira koneksi saya yang hilang, kan? Karena Bu Yeni tiba-tiba juga pausin.
Tadi ini deh mati listrik sebentar.
Iya. Mohon maaf, ini kita tunggu saja nggih sampai beliau bergabung kembali.
Ya. Kan ada WA-nya toh Mas, nanti kalau agak lama dipakai WA saja.
Bu Yeni yang ada WA-nya, Bu.
Iya. Iya, tadi dia juga
Ini
nulis
saya
di layar
coba.
itu.
Ini
Oh ya, oke.
sudah
Ya.
bergabung lagi.
Sudah ada. Halo.
Halo.
You are still mute.
Snaini, can you hear me?
Yes, very
Yes.
clear.
Yes.
Can you hear me?
Yes.
All right.
Can you
Sorry,
hear us?
I don't.
Oh, okay.
Yeah, I don't know what happened yet. So let me again share a screen, right? So is that okay?
Yeah.
All right.
Okay. All right.
Sorry that I don't know. It comes from my internet or something else.
Yep.
All right. So
Okay.
what I just what I was talking about the P group degree, as I mentioned, the P group degree means that the probability of a group to be a P group. So I just started with example S3. So S3 has 6 elements. Here is the order of elements. No, because order of S3 is 6. 6 is 2 times 3. So first of all, we can see that S3 is not 2 groups and is not 3 groups, because the order of S3 is not a power of 2 and is not a power of 3. Now, what we can say about the probability of S3 is 2 group or 3 group. So the D2 S3 probability of S3 to be a two groups. So we can count the number of elements of S3 which has the order, which their order are power of 2, right? So one of order is identity, because identity is 2 to the 0 is the power of 2. 1, 2, 1, 3, 2, 3. We have 3 elements of order 2 here. So we will have 4 elements of orders power of 2 divided by the all elements is 6. So we have 4 over 6 is 2 over 3. That's the two group degree of S3. Now, how about the 3 group degree of S3? So we have to count the number of elements which which their orders are a power of 3. Again, we have identity, right? And we have identity is 3 to the 0. You know, identity is in all P group degree because we can see P to the 0. 1, 2, 3, and 1, 3, 2, they have order 3. So we have 3 to the 1. So we have 3 elements of the just order power of 3 divided by the order of S3 is 6. So we have 1 over 2. So if you look at two group degree and 3 group degree, you can see that 2 group degree is the probability is 2 over 3, and 3 group degree is 1 over 2. And you can see that 2 over 3 is bigger than 1 over 2. So it means that the probability of S3 to be a 2 group is much bigger than to be a 3 group, right? Now, look at the dihedral group of order 8. So here is the orders. We have 8 elements, and the orders identity has order 2 to the 0. And we have 4, 2, 4. That's the list of orders. Now, the probability of group D8 to be a 2 group is the set of all elements which they have order of a power of 2, right? Divided by order of D8. So we can see that all elements of the dihedral group have order, they have order a power of 2. So we have 8 elements divided by 8 is 1. So what's the meaning of 1? The probability of D8 to be a 2 group is 1. So the equality 1 means that the group is 2 groups, right? So we can say that if G is a finite group, such that P divides the order of G. You know, if we are going to divide the probability of a group to be P group, so P must be divided the order of G. Otherwise, we don't have any elements of a power of P, just maybe only identity. So if G is a P group, then the P group degree is 1, and the conversely. And if the P group degree is 1, then the group is P group. So for this reason, I put the name P group degree. Is the probability of a group to be a P group. You can see that's just a proof. Now, let me give just notation for a group. Suppose that G is a finite group of order n. And if we give just, if we present n as just the composition of the prime numbers. So if n is P1 to the R1, P2 to the R2, until Pk to the Rk, right? Which P1, P2, and Pk are all prime numbers. So we can denote the pi of G is set of all prime numbers, dividing the order of n, right? For example, if we have 6, so the pi of 6 is 2 and 3, because we have only 2 and 3. If we have 8, so we have only 1 prime number, so pi of G is 2. Now, I'm going to define the prime order elements degree of a group. So it means that the probability of an element, of a group has a power of P. Let me introduce the second probability. So suppose that G is a finite group, and the pi of G is the set of all prime numbers dividing the order of G. So the prime, look at it, the prime order element degree of G, prime order element degree of G, we can denote by d prime of G by these relations. So that's the definition of the prime order element degree of G. You know, the prime order element degree of G means that the probability of an element of a group G has a power of a prime number. So the prime order element degree of G, we can denote by d prime of G. It is the number of elements like X in G, such that order of X is a power of prime numbers. Which prime numbers? The prime numbers which they divide the order of G is P1, P2 to Pk. So the number of elements X such that the order of X is a power of one of elements P1, P2, or Pk. So order of X, a power of P1 or power of P2 or power of Pk. That's the prime order element degree. Let me again give an example. So look at S3. You know, what I introduced at the beginning of my talk about the groups, because most of the time I'm using groups, S3, D8, Q8, and so on. So that was the reason I prefer to just remind non-groups at the just beginning of my talk. Now, S3 has 6 elements, right? So order of S3 is 2 times 3. So the pi of S3 set of prime numbers of S3 is the set of 2 elements, 2 prime numbers, 2 and 3. Now, the prime order element degree of S3, as I defined as above, is the set of all elements X is in S3, such that the order of X is a power of 2 or power of 3, because, you know, here look at the definition, the set of all elements X in G, such that the order of X is a power of P1, P2, or Pk. We have here only 2 prime numbers, 2 and 3. So the set of all elements of S3 such that the order of X is a power of 2 or a power of 3. Now, look at identity. Identity is a power of 2. So we will have identity here. 1, 2 is the power of 2. 1, 3 is a power of 2. 2, 3 is a power of 2. 1, 2, 3 is the power of 3. 1, 3, 2 is the power of 3. So all elements of S3 has a power of 2 or power of 3. So the prime order element degree of S3 is 1. So it means that all elements of S3 has a power of 2 or has a power of 3. Now, the second example is the cyclic group of order 6. So again, we have, 6 is 2 times 3. So we have pi of G is 2 and 3. So we have 2 prime numbers. So we have 6 elements here, 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar. And the orders is that the 0 bar is 1, which is 2 to the 0. 1 bar is a generator, has order 6, right? So we have 2 times 3. 2 bar has order 2, order 3. 3 bar has order 2. 4 bar has order 3, and 5 bar has order 6. Now, the set of all elements of the cyclic group of order 6, which has a power of 2 or power of 3. So we can look at here. We can see, all elements which has, so what we have to do is to consider all elements of Z6 which has order a power of 2 or a power of T. 0 bar has a power of 2, so that's okay. We will have 0 bar. 1 bar and 5 bar, they have order 6. They have not order of a power of 2 or a power of 3. So we don't have 1 bar and 5 bar here. But still we have 2 bar is a power of 3, 3 bar has a power of 2, and 4 bar is a power of 3. So the number of such elements, we have 4 elements divided by 6 is 2 over 3. So the prime order element degree of Z6 is 2 over 3. Now, here is that we can give a relation between the previous probability and this probability. So the prime order degree of G, as I mentioned, is the set of all elements of G such that the order of X is a power of P1 or power of P2 or power of Pk. So we can just split this set to the set of elements as order power of P1 plus the set of elements, the number of elements as order power of P2, right? And similarly, until the set of all elements of they have order of a power of Pk. We put identity in the first one and remove identity from the other because we count identity only 1 times, right? So look at here, the number of elements such that the order of X is a power of P1 divided by order of G is exactly Pi degree of G, right? And for the second one is the P2 degree, but we lose identity. So it means that that's the P2 degree minus identity. So the prime order degree of the group G is the sum of Pi degree of G from I to K minus K minus 1 over the order of G. K minus 1 means that we put identity for the first set and we remove identity from, so we have k minus 1 times which we remove identity. So that's the relation between prime order degree and pi order degree. This is the example for D6, right? So as you know, you remember I found the prime order degree directly. Now here we can use the above formula by using 2 degree and 3 degree. So D2 degree of Z6 is 2/6, and D3 degree is 3/6, right? And the pi of Z6 is 3, right? So by the above formula, we have K is 4, P1 is 2, P2 is 2. And if we put this amount in the formula, then we can get 2/3. That's the just the exactly prime order degree. Here are some results. So I don't know, I have time. Let me.
Yeah.
Maybe I
still 15 minutes.
Can give the results in the next week. Sorry that this lecture I introduced some of elementary concepts in group theory, and I'm so sorry for professors, doctors, and lecturers, because, and also PhD students, they know all about these concepts, and just I want to remind and recall from the notations only. Okay, so we have about 15 minutes for answering questions.
Thank you, Professor Erfanian. Maybe, is there any question? Actually, there is a private question from Dr. Diah Yunia.
Yes.
Maybe, Diah, do you want to ask directly?
Yes. So, can I stop sharing or not?
I think it's okay lah to show the presentation also.
Okay.
So actually I don't get her question. That's why if Dr. Diah, are you here? Not here. Okay. So the question is like this. I try to translate in English. When we deal with like a structure like monoid, semi-group, group, we always deal with binary operation. And sometimes it is difficult to teach to especially undergraduate students, because sometimes we know that the binary operation comes from a function, right? From that group, that set into that set. So maybe can you share how do you teach that kind of stuff to your student? Because
about binary operation?
Yes.
Yeah. Okay. You know, sometimes when I'm teaching about the just group theory, just the first lecture on group theory, we can use this way to introduce binary operation. Sometimes it's better to replace binary operation by the you know, if you have S and a star is a function. So we can say that S, the pair S and a star is a binary operation if S is closed under operation a star. So sometimes we may use binary operation by closed under operation, because what we have to do is if you take two elements, X and Y, so X star Y must be in S. This is very important. And we can put this property by the closed property. So sometimes I use this way to introduce a group. We can say that if we have a non-empty set S and a function S, then we can say that the S and S star is a group if we have 4 properties. The first one is closed under operation. It's exactly the binary operation because it comes from the function. So you may put a map instead of function. You can put S is a non-empty set and S star is a map. Then we can say S and S star is a group if we have 4 properties. So close under operation star, we have associativity, the second condition, we have identity elements, and we have the inverse. So we can put 4 elements. Here is much better because sometimes we may have not binary operation because sometimes the multiplication or the multiplication of 2 elements in subset S under the map S star is not necessary to be in S, right? So here we may put the closed instead of the binary operation. This is my my experience, but I don't know. You may explain more, and Prof. Uni maybe explain much better than me.
Yeah, actually, Prof. Uni also has a question.
So, oh yeah,
yeah, yeah. I wrote on the chat. Yeah. So thank you for a very interesting introduction on group and probability. I never boring because it's
sorry about that.
Maybe I missed some. Why? I have a question. Why in defining probability you assume the P is prime? Is it because of Lagrange theorem or it's okay? That's my question.
All right, just let me give your question in general way. So I may say yes. That why the probability is important in group theory, because there are some probabilities. Of course, some of them are not very important, but we have some important probabilities. The main point is that let me give an example. If you take a group, so if a group G is abelian, right? For example, we have results about the nilpotent group. We have a main theorem that, right? If a group G is abelian, then the group is nilpotent, right? Now, what we can say about non-abelian group? Now, I will define in the next week about the commutativity degree. Commutativity degree means that the probability of a group to be abelian, it's the number of pairs which are commute, but the total number of pairs, right? Now, if we use the probability, then we can improve this theorem to this way. I will prove that if G is a non-abelian group, but the commutativity degree is bigger than half, then the group is again nilpotent. You know, I use the tool in probability to improve a theorem because the theorem says that if a group is abelian, then the group is nilpotent. So they can't say anything about non-abelian group. Of course, we have something about non-abelian group, but non-abelian group with some more properties. But the probability is much easier to compute the commutativity degree, right? So if you count the commutativity degree, then you can see, and if the probability is bigger than half, then it's easier to see to say that the group is nilpotent. Otherwise, you know the definition of nilpotent group. So you have to just find the central series, and you have to check central series about the property of nilpotency. You know, you have many things to prove for the nilpotent group. but by very easy tools, which is the probability, you can improve a theorem. So that's the motivation of the importance of the probability, right? So we may introduce some more probabilities here, but the main point is that the probability is important here, which we can use this probability to improve some results, some theorems in group theory. That's my motivation about the probability. Prof. Yuni, is that satisfy you? Or
Yeah. It's okay. Now I understand the reason why you assume the P should be prime. Yeah. Okay.
Yes.
Yes.
Thank you, Prof. Yuni. Is there any more question? If not, I would like to ask also. So, yeah, thank you
Let
for.
me ask you. Let me ask you. You are lecturer or PhD student or something else?
You
are lecturer.
Yeah.
Oh, that's great. All right.
Yeah.
Because
Can I ask
the first
you?
one, I have to see your position, because I have to see that you know more about the group theory or something like that.
I'm junior in this
you may ask.
laboratory.
That's great.
Yeah, I'm curious about thank you for reviewing many types of groups like Dihedral Group, Quaternion Group, and so on. But I'm curious about how to link a graph with a group, especially if the group is infinite, because there are many infinite groups. And is it possible to link a graph with a group with infinite number of elements?
Yes. You know, if you want to define a graph associated to a group, of course, you are hurry because that I will explain in the next week about the graph. But you are going to know earlier. You know, if you want to define a graph associated to a group, so we have two important things. First one, the group is finite or infinite. It's very important, right? So if the graph, set, if you take the vertex set of a graph associated to a group is is always depends on the number of elements of a group, or you know. So the first one is a group G is finite or infinite. It's important. The second one is what's the vertex set. So sometimes the group is infinite, but the vertex set is not the all elements of the group G. Maybe it's the number of all normal subgroups of group G, right? So it depends on definition of the vertex set. We have sometimes the group is infinite, but the vertex set is finite. So the infinite or finite of a graph depends on the vertex set. You know, we have infinite group. We have, you look at definition which I mentioned about the P element degree. We may have a P group, infinite P group, but all elements, when we say the P infinite P group, it means that the order of each element must be a power of P. It means that the order of each element is finite, right? So the infinite or finite of given graph depends on the vertex set. So if the vertex set is the set of all elements of G, so if the group G is infinite, so trivially the graph, we have infinite vertices, right? So it's important on definition about the graph. So definition will actually explain that the graph is finite or infinite. Usually, because we mostly computing some properties of graph it's better for the beginner to start with finite graphs. But of course, we may have more algebraic graphs with infinite vertex sets, so they have infinite graph.
Okay, thank you. I think that's very clear. Okay, maybe another question from participants. Or do you want to raise your hand, or do you want to turn on your mic? That's also fine.
Yeah,
Okay.
I just like to continue the question about your explanation, Prof. Erfanian.
Yes.
After we, for example, know that the group is, the probability this group is abelian is 1.5. So what would we expect for the future, for the next research? I mean, you give the example that abelian group is nilpotent, yeah. But if what happens if the group is not abelian? So, for example, the probability of the commutative probability of this group is 1/2. So, what we expect for the next research, for example?
Yes. You know, in the next week, I will talk about the commutativity degree, and you can see that what's the importance of the commutativity degree. We will have, you know, if the group G is abelian, so trivially the commutativity degree is 1, right? So the main point is that for non-abelian, what's the commutativity degree for non-abelian groups, right? So if the group G is non-abelian, so the probability is something between 0 and 1, right? Now, in the next week, I will prove that if G is non-abelian, of course, we are talking about the finite group because Snaini likes infinite group, but now we are talking about the finite group. Yep. So if G is finite and non-abelian, right? So we will give an upper bound for the commutativity degree. And I will prove that the commutativity degree is at most 5/8. 5/8. So it means that if we have a group with the commutativity degree bigger than of 5/8, the group must be abelian, right? Now, right now, 1/2 is important for the commutativity degree because there is a theorem which says that if the commutativity, we are talking about non-abelian group, if the commutativity degree is bigger than half, then the group is nilpotent. So that's the importance of 1/2, because if it's less than 1/2, so it's not necessary to be nilpotent. And we have some rational numbers, right? Some rational numbers, for example, for soluble groups. So we can put a number if the commutativity degree is bigger than that rational number, then the group is soluble. It's important, this result, because you can use very, very easy tools to improve that the group is nilpotent. Look at the definition of nilpotent. If you want to prove that a group G is nilpotent, what you have to do? You have to define a central series. So the central series means that you have to know more exactly about the list of subgroups, because you are using to use the subgroups to construct the central series, right? So if you don't have more familiar about the subgroups, so you are not able to prove that the group is nilpotent, because you first have to provide a central series. and then check that is the condition for nilpotency is satisfied or not. So what the commutativity degree is very easy. So you can just count elements and see that what pair of elements they are commute. You know, it's very easy. You can use some, not only by hand, maybe by some software, algebra software like mathematical, like gap, to use the group is nilpotent or not, right? Because you can easily find the commutativity degree, right? For example, we may have a group of order, for example, 1000. You can easily find the commutativity degree, right? Because you have to compare every two elements. You can use a software, for example, gap or mathematical or something to find the commutativity degree. And if the commutativity degree is, for example, 2/3, then you can easily say that the group is nilpotent, right? But if you want to use the direct way to prove the nilpotency, is very difficult because you have a group of 1000 elements. So we may have many subgroups. So how to use subgroups to find a special central series having the property of nilpotency. So that's the motivation of commutativity degree or other probabilities, because the computing of probability is much easier to prove a property for a group, because it's just very easy to compute. That's just my explanation. I don't know, is that enough for you?
Yeah, so we have another way to prove something, yeah.
Yes.
Okay.
Yeah. So the important things in probability group theory is to use some probability tools to prove some theorems in group theory, you know. And similarly, we can say something about the graph and groups. Sometimes we may define a graph, and instead of prove that the group is abelian, you can prove that the related graph is a complete graph. You know, different way to prove. The theorem is in group theory, but you can use by graph theory tools or probability tools to prove that. This is the interdisciplinary topics between 2 or 3 subjects, you know?
Yes. It's very nice. Yeah. Thank you for your explanation.
Right.
Thank you.
Thank you.
Okay. There is one more question from Mr. Rian Wicaksana Putra. You want to ask directly?
Yes.
Okay. Mr. Rian.
Yeah, thank you, Mr. Hello, Professor. I want to ask, you have explained 8 types of group. I want to know if we are only working on this 8, or there are another group that we can work on when we are constructing some graph from groups. Thank you.
You know, first of all, the groups which I introduced here is just some of known 9 types of groups. You know, we have many other kinds of groups. So that's some important examples of groups, because when we are talking about the graph theory, a graph related to groups, we have to give some examples. So this kind of groups help us to give example much easier, because for that you know the definition of, for example, dihedral group, symmetric group. That's the reason which I introduced them. But we have some more groups. You know, we have many groups in group theory. We don't have only 7 or 8 types of groups. We have many other groups in group in group theory, but we don't have time to introduce all of them, and we don't need to use all of them in graph theory, because it's easier to use some easy examples to explain a graph associated to a group. That's only some of non-groups which I prefer to introduce here, because we have many groups, and of course in some project which I'm supposed to give you in the next in the second parts of my lectures, is to compute and find my probability, or also some properties of a graph for some groups, not only these groups which I include, some other groups, right? But that these groups are enough for my explanation about algebraic graphs. But we may have many groups. You can try for your interested groups with these definitions.
Yeah, okay, thank you, Professor.
All right.
Okay, I think that's a bit clear. Because we run out of time, maybe this is the last one from Dr. Yani Susanti. So please.
Thank you very much, Professor Erfanian, for your interesting lecture today. Actually,
Thank you very much.
Yeah. Actually, I'm curious how far the development of algebraic graph associated to semi-group is. Or maybe
yes.
Could you give us some outlook to this question? Thank you in advance.
You know, algebraic graphs means the graphs associated to an algebraic structure. Algebraic structure, it doesn't mean the only group. Algebraic structure, we may have a ring, we may have a semi-group, right? We may have just some other algebraic structure, because we may define a graph to a modules, right? To our modules, to a vector space. And we have some graphs associated to a semi-groups. One of them, which I will touch about that probably next week, about the Cayley graph, right? You know, the Cayley graph is defined a graph related to a group, was we have replaced group by semi-group, right? So we have, and that's the reason that the Cayley graph defined for a ring, not only for groups, because they define for the ring. You know, the ring is a semi-group under, if you take the multiplication for a group, then you will get this, the semi-group, right? So I think you may wait another week to just explain something more about the algebraic graph. I know you have many questions about what's the algebraic graphs, and if every of you interested to define a graph related to your interest of algebraic structure, because some of you working on group theory and some of them working on maybe ring theory, on module theory. So we can define these of graphs, but first of all, you have to get more familiar for some algebraic graphs, and then you can try to define a new graph by yourself in your area of algebra. We have some graphs related to semi-groups, yes. Okay. So in the near future, I will introduce some of them.
Okay, thank you very much. Maybe when just responding your answer, I and my student Niswah is also here.
right?
have read your paper on bipartite graph associated to elements and coset. Is
Yes.
it yours, right? Yes, and
Yes,
and
yes.
I and Niswa have a discussion on this, and like if it's possible to replace the group by a monoid, and we try to do this, and we wonder if it is already done before or not. It is already done or not? Yeah.
No, it's not, because that graph is new. I published last year, and you know, the graph we consider a group, and the coset. For the coset, we need subgroup. So first of all, if you replace the group by by monoids, so what we can say about the subgroup, because we have to consider the coset of subgroups, right?
Yeah.
So
is it possible to replace subgroups here by sub-semigroups of the monoid? Not necessarily sub-monoid, but only sub-semigroups. What do you think?
I have just better way to do something on this. So it's not necessary to replace the group by semigroup. We can just do something else. Like, so let me explain private to you about your student. I will give some new ideas. Because if you replace the group by semigroup, you will lose something, because you are not able to talk about the inverse of elements. So you can not able to define the subgroups. So what we can say about the concept of subgroup, you know, you will lose many things, but sometimes you can say something else. I will explain it to you sometimes.
Thank you.
All right.
Yeah, thank you very much.
Okay. Thank you very much, Professor Erfanian, for sharing with us today. And yeah, let's give him a big applause. Okay, I think that's the end of our program for today. Thank you very much for everyone for the active discussion also. That's really nice. And yeah, see you next week at the same time. I think that's all. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.